Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 16.1, so we are starting a different technique. And in this section, we're going to introduce into limit integrals. Yes, this is where the fun and the nastiness begins, and the craziness stuff. So in this section, we're just going to do some basic limit integrals, so nothing too obscure. So it's just going to be a basic limit integral, or a good introduction to limit integrals. Okay, so let's go ahead and get started with some examples. Alright, so the first level of dealing with limit integrals, is L'Hopital's rule. Okay, that is the easiest type of limit integrals we can ever have, is L'Hopital's limit integrals. So, how is this L'Hopital's? Well, it's because if you plug in 1, you get 0 at the bottom. This integral is technically a numerator, or at the top, per se. And if you plug in 1 here, this integral becomes 0, because from 1 to 1, that just makes the whole integral 0. So, because this is technically 0 over 0, we can use the L'Hopital's rule. And so, here the derivative at the bottom is just 1. So, in other words, we are literally deriving this integral here. And we use the fundamental theorem of calculus. We derive this integral here. And so the derivative of this is just simply square root of inverse tangent of n, right? So this is evaluating at n equal to 1 because the limit approaches to 1. And so what we have is this is inverse tangent of 1. This is equal to pi over 4, square root of pi over 4. The answer is square root pi over 2. Okay? Just simple L'Hopital's rule. Alright, let's go ahead and do some more examples of these. Don't freak out. Alright, a lot of these limit integrals, they're always gonna look ugly, or they look monstrous. But don't freak out. They're not too bad, at least. Well, some of them aren't too bad, but so here we clearly see that this is a L'Hopital's rule because 0 here, and if we plug in 0, this integral also equals to 0. So we go ahead and apply L'Hopital's rule. So when we derive, the bottom is 3n squared, and on the top we get sine of n squared. Okay, so cool. So this is what we have. Alright, so at this point we are literally just playing just limits at this point. So how do you solve this limit? You can do L'Hopital's rule, but I'm going to do the G-main way, and that is utilizing a baby limit theorem. Not really a theorem, but just this baby limit. I'm going to take advantage of this property. Whatever you have this, whatever this is, this will always equal, well, I shouldn't say function, that's too a little too OP. Let's say just in general, this is equal to 1, right? And if you have anything else, any function that equals to 0, any function that equals to 0, when you plug in 0, this is equal to 1. Okay? So, I'm going to take advantage of that. So to solve this limit, I see we have sine of n squared. So that means that I need sine n squared here, but then I need to put sine n squared at the top, which is perfect because I do have n squared here. So this is 1, this is 1, so my answer here, this integral, this limit integral, equals to 1/3. Okay? So you could do baby formulas like that. Okay? Like if you know that, oh, well, I know that e to the n minus 1, where n is equal to 1, right? Then you could take advantage of when you're solving limits like this, right? Or something nasty, whatever, I don't know. Right? You could take advantage of this, use baby limits and like apply it. Okay? So that's how I kind of get away from like disgusting L'Hopital's rule. Okay? I think you'd still use L'Hopital's here, but I'm just lazy. Okay? Alright. Next integral. Infinity. Okay. Now, this is where scary things comes in. You're probably thinking, wait a minute, that's infinity. Infinity here. Wait, okay. I don't see any L'Hopitalness here, so what on earth do we do? Okay. So, let's go ahead. Let me reformat this. So that's e to the negative n squared. So what we have is we could separate that like this. Okay. Now, is this L'Hopital's rule? Is this L'Hopital's rule? The answer is yes, and it's actually, well, a lot of people might say this is trivial, but I don't think it's like, I wouldn't say this is exactly obvious to see, because here we plug in infinity. It's not like 0, right? But here we have infinity. This whole portion, this is technically infinity, right? So we have infinity at the bottom, but is the top infinity? And yes, it is. And let me tell you why this integral is considered equaling infinity. And the reason is because this function, well, I don't even have to draw a graph actually. This function, e to the x squared, is an increasing function. This is an increasing function, meaning that e to the x squared, I don't even know what this graph looks like, but I know it's going to be like, whatever. Something so high up, whatever. Something so high up. So, yeah, it's gonna look like this. As we go from 0 to infinity, you know, the area under the curve has to be infinity as well, because it's an increasing function. This graph ain't gonna come down, of course not. So it's an increasing function. So this integral, when you integrate it from 0 to infinity, this whole area is going to equal to infinity. So with that in mind, this is equal to infinity. So, and is this allowed? Yes, it is. You can. It is allowed that you can apply L'Hopital's rule like this. Okay, it is justified. So we go ahead and apply L'Hopital's rule. So here, be very careful because you actually have n times this integral. So what that means is we actually have product rule. So we have 0 to n ex squared dx plus n times e to the n squared. Okay? And then this is 2n e to the n squared. Okay? So be very careful with that. N times an integral. This is product rule. Okay? So now what? What do we do now? So we know this portion here, this right side, that's equal to a half. A half plus, but then we still have this limit that we have to deal with, right? Of course, we could do L'Hopital's rule again, e to the n squared, right? But then this whole portion, it's product rule. So e to the n squared plus n times, well, 2n squared e to the n squared. That's what we have here. Okay? And so now we have half, and then the limit as n goes to infinity. Well, we can actually now divide e to the n squared. So what we have here is 1 plus 2n squared. Yeah? And this is all just 0. Because n squared exists. And so we plug infinity, this all goes to 0. So the answer is that this limit integral is equal to 1/2. It converges to 1/2. Okay? So there you go. So yeah, this is a tricky thing to be aware of, right? You know, if you see an integral like this, up to infinity, ask yourself, is this an increasing function? Or at this interval, at least at this interval, is the area under the curve infinite? And if it is, you have the rights to use L'Hopital's rule. Okay? And then here, also be careful when you have an n times an integral, it is product rule. Okay? It's not a constant that you just derive, no. This is product rule. Okay, so be very careful with that. So we have this limit integral, 1 over n squared. There's no bounds. So what do we do? What on earth do we do? And this looks weird, right? This doesn't look integrable. So when you have a non-integrable integral, then you do limit first. Right? If the limit looks hard, but the integral is easy, do the integral first and then compute the limit. Okay? So you can always interchange. Okay? There's a speed integration. We don't have to worry about real analysis stuff because honestly you don't get judged in that in this sport here. So here, you know, if the limit is easier, do the limit. If the integral is easier, do the integral and then the limit. Okay? In this case, this integral does not look integrable, so we're going to do the limit first. Alright, so I just want to keep in mind this is parentheses, so it's 1 minus cosine of this times cosine rather than 1 minus cosine times cosine. Okay, so I'm just going to put a parentheses like that just to be safe. And now let's go ahead and compute this limit first. So let's go ahead and combine this. Okay. So we have cosine nx. We'll bring the 1 in too, because 1 over n squared, that's infinity. So we're going to have to bring this in so that, well, would you look at this? Now we can use L'Hopital's rule, right? So 1 minus and then 1, and then this becomes 0. So 0 over 0, so let's go ahead and use L'Hopital's rule. Now, be very careful because we have x's. We have x's right here, so you have to be very careful. You're not deriving x, you are deriving n. And so x is treated as a constant here. Okay, so let's go ahead and apply L'Hopital's rule. So we have 2n right off the back at the bottom. But here, what is this? What on earth is this? How on earth do we derive? What is the derivative of cosine of n to the power of x of cosine nx? What on earth is this? So, again, it's okay to, to be very careful. We have x minus, this is x. Cosine of n, x minus 1. And then we have sine of n, negative actually, this would be negative. And then times cosine of nx. And then plus, and then now we have to derive this. This is also negative sine of nx times n with cosine of nx. Okay? If you need to, just write it long. Don't try to simplify anything, just write it long. And now, here, the negative, thankfully, the negative cancels out with this negative. And so what we exactly have is we have cosine, well, this is x, cosine of n, x minus 1, sine of n, cosine of nx, plus sine, n times sine of nx. This is a mess, I know. I don't blame you. Okay? Now, first of all, I see sine of n's, and I'm gonna divide n to both sides so that I can make this a lot cleaner. So sine of n here, we have n. So I'm gonna separate this, x over 2. We have cosine of n, x minus 1, cosine of nx, plus, and then n gets cancelled out by this. So we have a half of sine of nx, cosine of n to the power of x. Can we plug in 0 now? Yes, we can. For the love of God. Yes. So plug in 0, we get 1, everything here. So this is x over 2. And then plus, and then plug in 0 here. Everything is 0. So what we have is the integral of x over 2. Wow. So our answer is x squared over 4 plus c. And this is our answer. Okay? Jesus. So, again, if you need to, you can go ahead and get out of the solving field and just find the derivative if you need to. And then you can go ahead and implement it. And then, whenever you're safe, go ahead and finally plug in 0. And, yeah, you're good to go. And like I said, baby limits is super helpful. Baby limits, well, sine of n over n. Sine over n over n, this was helpful. Baby limits, use baby limits. It's super helpful. Okay? We have this limit integral now. Now you're probably thinking, okay, how on earth are we going to do this now? We have 0 to infinity, cosine to the power of infinity of x over square root of infinity. How do we go about this? This does not look like a L'Hopital integral at all. So what we're gonna do, so it's important why we learn loophole logs. So we're gonna do that. Let's go ahead. Whenever we see something funky like this, a function to the power of a function, whatever, we use loophole log. So let's go ahead and do that. Limit of n to infinity. We're going to go ahead and do a loophole log e to the ln. So that's n times ln of cosine x to the power of square root of n dx. Okay. Cool. What now? If we plug in infinity, it's a little strange because you can't exactly. We have n here. So how do we go about this? How on earth do we go about this? So we can actually focus on this first, right? Don't worry about this n. We can actually. It's kind of like it's like a weird way of saying let's separate this. So like if we have a limit and we have like f and g, but it's like configuratively like constructed weird. You could separate it in a way where f is convergent and g is convergent, and we can just separate it however, right? As long as they both converge. The way you separate it, they both converge. Then you can go like this. So, but it's weird. It doesn't look like that here because it's an integral form, and it's like mashed with this function. So I get it, but it's actually this is allowed to do. So if we plug in infinity here, 0 ln of 1, 0 times infinity. Looks like we are using L'Hopital's rule. So let's go ahead and use L'Hopital's rule. So we have the ln, well, this would be e technically, of cosine of x over square root of n. I know this looks nasty, but let's grow some balls and solve this. So if we derive this, okay, if we derive this, we get negative tangent of x over square root of n times the derivative of x over square root of n. This is x because that's a constant, but the derivative of 1 over square root of n, this is what, negative n over what would it be? I can't do it in my head. Negative half. So we have negative half, negative 3 over 2. I think that's correct. Yeah, with x. Yeah, and then we have negative 1 over n squared. Okay, so now if we simplify this, so now when we simplify this, this should look like what, tangent. The negative cancels out. Well, negative cancels out. So we still have a negative. Tangent of x over root n, and then over 2 with this 2 here, and then we have x of, and then n squared. 2 minus 3 halves, that's a half. So we have square root of n, and this is also a negative. Okay. Okay, let's keep going. Let's keep going, keep going, keep going. E is the limit, n goes to infinity. Okay, be careful not to drop the negative, x over 2. And what we have here is we have tangent of this, of over square root of n. We're going to go 1 over root n like this, because I know for a fact that we still have to we still have to do the L'Hopital's, because we have infinity times 0. So let's go ahead, and when we apply, let's see, sine of, I noticed sine of, if we turn this into sine, right, sine over cosine, I noticed that, let's see, if you let x times x, right, that's going to be 1, and then left with cosine of x over n. That's going to be, plug in n to infinity, it's 0. Cosine of 0 is 1. Aha! I got my, yeah, so if we compute the limit, n goes to infinity, and now we have e to x squared over 2. Right, so this is what we have. So we have this x from the baby limit, like I said, baby limits. Use baby limits, it's so helpful. So helpful. Now we have negative x squared over 2, and we have, this is our integral. And when you look at that, this is simply a Gaussian integral. So this is what? Root 2. When I do u equal x over root 2, yeah. So, and then it becomes a Gaussian integral. So, root pi over 2. So our answer is the square root of pi over 2. Okay? That is our integral. Okay? Very scary. Not gonna lie, this is, this looks daunting. But, if you just treat it like limits, if this is a disgusting whole integral, go ahead and do the limit first. And as you can see, with this limit, we have to use L'Hopital's rule by using loophole log. Okay? Very sneaky, very tricky. Okay? And this whole L'Hopital rule, it's tedious, but, we got over it. It's not too bad. Could have been worse. And baby limits, I can't express to you enough how important and how fast it is to just use baby limits. Okay? Alright, let's go with our last integral. Alrighty, this is our last integral, our last limit integral for this section. And it seems like a L'Hopital's rule right off the bat. You can immediately notice 0 at the denominator from 1 over n, and then the 0 from the integral, plugging in from 0 to 0, this whole integral is going to become 0. So immediately we, L'Hopital's rule. All right, so that's going to be, this bottom's going to be 1, and if we derive it, we get 1 minus tangent of 2n over, to the power of 1 over n. Okay, and now this is just, at this point, it's a limit problem. Okay, so this is just a limit problem. And then, like I said, a function to the power of a function, use loophole log. Okay, we'll go ahead and do that. Use loophole log. We immediately notice that this is going to be 1 over n ln of 1 minus tangent of 2n. And here at the exponent, that's a L'Hopital's rule, a simple L'Hopital's rule, right? So this is what? This is going to be 1 e to the 1 minus tangent of 2n with negative 2 secant square of 2n, right? And then if you plug in 0, this is all going to equal, well, the limit is n approach to 0. The limit, if you plug in 0, 1 minus 0, negative 2. So our answer is 1 over e squared. Okay, done. See how fast that is? Now we're learning how to solve limit integrals super quickly. Okay, and this is just the basics. This is like the first step, the first level of solving limit integrals. Okay, cool. Now I do want to make a quick mention. Let me go back all the way. Do want to make a quick mention. If you're bound, okay, if you're bound, let me actually change the bound on this. I don't know if this converges, but if your bound is like nonlinear, let's say n squared here, and let's say n here. Okay, so you have two different functions on your bounds. Then the way this works, the way you derive an integral is, well, if we apply L'Hopital's rule, this is just going to be 1. So with fundamental theorem of calculus, when we derive something like this, okay, it's kind of, it's chain rule. So this is chain rule. So what you do is you plug in 2n squared. So this is, when you derive an integral, it's just this. But now it's 2n squared, 1 over n squared. And again, it's chain rule. This is chain rule. So because you have n squared, it's times 2n. And then because of this bound that you have, this is now minus, and then 1 minus tangent of 2n, 1 over n. Okay? So this is from the top bound, this is from the lower bound. Okay? So that's how you derive crazier integrals like this. Okay? And if this is not a linear function, like this, then this, you have to use chain rule. And that's where the 2n comes from. Okay? So I just want to keep that in mind. I just want to give that to you. I believe this is, I don't know if this converges. I know this is 1 over e squared, but I don't know if this converges. If you multiply 0, well, you would have to see where this goes, unfortunately. And I'm curious, actually. ln of 1 minus 2n squared. Does this go anywhere? 2n. This goes here. 2n squared. And then the derivative, secant square, negative 2n squared times 4n. Wow, it actually does converge. That's crazy. Okay, so we get 2. This is also negative 2. And then, oh, wait. This is 0? Because this is also 1 over e squared. So I guess this integral equals to 0. Well, there you go. I could be wrong though. I feel like I miscalculated somewhere. But I just want to show you this because this is, in case if you have a different kind of bound, right? Don't forget chain rule. Okay, chain rule and then treat it like integration. Don't get this minus sign, right? Upper bound minus lower bound. Okay? Alright, and that's about it for this section. So I hope that helps. Again, go ahead and practice so that you become more comfortable with limit integrals and to get rid of that fear of that nasty looking limit integrals as well. So yeah, I hope that helps. Thank you so much for watching, and I'll see you guys in the next part.